So now look in this part B, that when the pressure in both the systems, when the valve was open, the water vapor starts to move from high pressure to low pressure, and when equilibrium is reached, the pressure in this vessel A and in vessel B becomes 1.22 kilopascal. Now if we go in the steam table and look that what would be the saturation temperature at this pressure of 1.22 kilopascal, as here it is in megapascal. So the saturation temperature across this will be 10 degrees Celsius. So in this vessel A, water is at 10 degrees Celsius. So if the outside temperature, which we have stated in the first case also, that in this system the outside temperature is 30 degrees Celsius. So it is very much evident that it will extract, or it will take the heat from the outside, and it will start boiling, and the water vapors, or the water will start evaporate, and it will try to collect in this section. So likewise we have said that some substances have a great affinity towards, or more affinity for another substances at some temperature and pressure conditions, and less affinity for other substances. So अभी समझो कि अगर सारा ही water evaporate हो गया, so this vessel will become empty, and this lithium bromide solution with water will also become saturated at one point of time. So this will be an intermittent system. So if we want to continue this system or to run this system, so we have to continuously supply this water in the reservoir A, and likewise we have to replenish this lithium bromide solution every time. So this was mentioned here. When a solute is dissolved in a solvent, the boiling point of the solution is elevated. So now moving further, the difference between VCRS and VARS. We have seen that VCRS consists of four major parts: condenser, expansion device, evaporator, compressor. So we have two pressure sides. At one side we have condenser pressure, another side is at which the evaporator is working, that is evaporator side, or evaporator pressure, or low pressure. Now this was the mechanical compression, because we have to compress the saturated vapors from low pressure to the high pressure, from PE to PC. Whereas if we see in this vapor absorption system, this one component of mechanical compression is replaced with four components in vapor absorption system. Now these four components are absorber, expansion device, generator, and the solution pump. Now if we look in this diagram, अभी देखो ये तीनों डिवाइसेस तो वही हैं: कंडेंसर at high pressure, expansion device, evaporator at low pressure. So this is the part in which we have to attain the lowest temperature. Now the mechanical compression thing is replaced with the thermal compression. That means we will compress our working fluid thermally, and thermal or via low grade energy. This was the major difference. So now look in this diagram. We will start with this system from evaporator. From the evaporator, the vapors will come inside this absorber. And what this absorber is having, this is having a weak solution which is coming from the generator. Now what is this weak solution? So let's suppose it is having an affinity for this refrigerant. So when the weak solution is coming, that means in this weak solution very less refrigerant is there, and it is having more affinity to extract the vapor refrigerant. So what it will do, when the weak solution will come here, it is having more affinity to extract the vapor refrigerant. It will absorb the refrigerant which is coming out of the evaporator, and we all know that absorption is an exothermic process. So here heat will be liberated, and that heat is sent outside at the ambient condition QA, the heat extraction in the absorber. Okay, now after mixing with the weak solution, the refrigerant vapor becomes a strong solution of liquid. Now this strong solution is pumped inside the generator. Now you will say कि पंपिंग में भी तो हमें वर्क करना पड़ेगा, बट अब समझिए कि वर्क ऑफ पंप, if we see in a closed cycle that pumping work is given by VDP, so the specific volume of the liquids is very less. So we need not to do very high work. That would be very less as compared to the work which we will do in compressors. So we will pump this strong solution inside this generator. Now what is the purpose of this generator? This generator separates the strong solution which is coming from the absorbed in two parts. It will separate the vapor refrigerant at high pressure and high temperature, and the remaining part, which is a weak solution of the liquid, it will again separate, or it will again send back to the absorber through this expansion device. Now how it is doing? Generator is basically using the low grade energy, that is QG. So it requires heat to separate the two parts of that strong solution. One is vapor, another one is this liquid, which is again expanded back to the absorber. So अगर मैं बात करूँ यहाँ पर QG की, तो जनरली QG हमारे पास अबंडेंस में अवेलेबल है, जिसको हम जनरली रेफर करते हैं लाइक we have solar energy with ourselves, we have so many processing heats, like समझिए कि एक थर्मल पावर प्लांट में या कितनी भी इंडस्ट्रीज में हम काफ़ी सारी वेस्ट हीट हमारे पास रहती है, so we can utilize that and send inside the generator. So in the very large industrial applications where we are having the heat in the chimneys, so we will, instead of giving in the atmosphere, we utilize that heat in the generator to separate our solution of vapor, high pressure, high temperature vapor, and the remaining part. So this is a major difference between VCRS and VERS. You have seen that we have replaced the mechanical compression of compressor with a thermal compression. So that would be more appropriate if you will represent the vapor absorption refrigeration system with this diagram. Now moving further, the next major part of this lecture series would be to calculate the maximum COP of ideal absorption refrigeration system. We all have seen that when we all have studied the vapor compression refrigeration system, then we have calculated the Carnot COP of the VCRS systems, and which we have seen that Carnot systems or VCRS systems run between two temperature limits. One is the condenser temperature and another is the evaporator temperature. So in between these two temperature limits, we have seen that the COP of Carnot refrigerator was the desired effect which we get in the evaporator, that was TE upon the work input which was T higher minus T lower. So Tc minus Te, and this was the COP of the vapor compression refrigeration system. Whereas in the VARS system, vapor absorption systems, we have three temperatures. You all will see. So this is a system VCRS. We have made this diagram. So in this system VARS, we have seen we are getting the heat from the generator, or in the generator, in fact, that is QG, which is at a temperature TG, generator temperature. We have a pump which is working continuously, that is represented by WP. So pump input, work input to the pump. Another is evaporator, where the heat absorption or extraction is there, heat absorbed at the evaporator temperature TE. And another is TO, that is the ambient temperature. So we all have seen that in vapor absorption system, we generally send or we generally reject the heat in these two systems. One is at the condenser QC at TO, ambient temperature, and another one is the absorber, because we have seen that absorption was an exothermic reaction. So in the absorber, the heat extraction is, or heat rejection to the atmosphere, is QA at temperature TO. So this is this diagram. So very carefully read these QE, QG, QA and QC. So this diagram states the energy transfer in a vapor absorption refrigeration systems. Now moving further, according to first law of thermodynamics, we know del Q is equal to del W, and from this relation we can write QE plus QG, QE plus QG, heat addition, QE plus QG positive, minus QC minus QA, minus QC which is going out of the system, जो हीट निकल रही है बाहर सिस्टम से, QC है कंडेंसर में और QA है एब्जॉर्बर में एट टेम्परेचर TO. सो हमने यहाँ पर इसको दिखाया है माइनस QC, heat going out from the system, and minus QA in the absorber, plus WP, work done on the system, that is plus WP. From the second law of thermodynamics, we also know that the total entropy change of the system is basically a summation of the entropy change of the system plus entropy change of the surroundings. And what we generally write it, this statement, that is equal to or greater than 0. We have seen that net entropy of change, we have learned that net entropy of change for a reversible system is equal to 0, whereas the net entropy change for an irreversible system is always greater than 0. So that's why we generally represent this statement with this inequality greater than equal to 0. Moving further, so we have seen that in this system, as the system operates in a closed cycle, so the entropy change of the working fluid of the system is 0. So delta system becomes equal to 0, and delta surroundings can be written as, from the Clausius inequality, we can write this entropy as we generally write heat as TDS. So we have written this delta as surroundings, QE upon TE minus QG upon TG, because if we take this QG and TE, now we will take separately this system and separately this system. So heat is going out, heat is coming out, so minus QG upon TG minus QE upon TE plus QA plus QC upon TO, that is greater than equal to 0. So from first equation or state first law of thermodynamics,